Hello everyone and welcome to another video. So today I'd like to continue our discussion on line integrals by introducing the idea of potential functions, which is going to allow us to look at how we can apply the fundamental theorem to line integrals. And that's going to lead to this idea of path independence or conservative vector fields. So I know this looks like a really long title, but these are actually pretty quick concepts, so this isn't going to be too bad. Obviously what we're going to recommend is that you've watched our previous video on line integrals, because we're going to build on a lot of those concepts, right? In this previous video we just talked about what is a line integral, how to compute it, but now we're going to look into some more details, okay? So the first thing I want to look at is this idea of potential functions. So for the potential function discussion, again, I hate to keep heaping on prerequisites, but please make sure you've watched these two videos. So watch this one here, which talks a little bit about some of the differences between scalar functions and vector functions, and then make sure you've watched this second video here as well. This is talking about the gradient and the directional derivative. Really, we just care about the gradient for this discussion. So unfortunately for this discussion, make sure you have these three prerequisites out of the way, namely the line integral video, the scalar and vector functions video, and then the gradient video. So if you're happy with all that, let's jump into this idea of what's known as a potential function. So the idea with a potential function is actually really quite simple. Some vector fields or functions, they've got this nice property, and we're going to see it's a benefit later on down the road, where you can actually obtain that vector field or that vector function by taking the gradient of some scalar function. So in other words, this is the expression or the equation that is true in the case of a potential function. So namely, you have some scalar function here, and if you take its gradient, you get the vector function in question, right? So in this case, if this is true, then we call this function f. That's called a potential function of the vector field v. Okay, so let's look at a quick example of this. So let's say you've got some vector function or some vector field that looks like this, right? So it has this x component, this y component, and this z component. And as you see, the x, y, z components, they change as you vary x, y, and z. Okay, so here's some three-dimensional vector function. Now, we can ask ourselves, well, what if you also consider, let's say I've got some magic scalar function f right here. Okay, so this is a scalar function. You put in x, y, z, it just spits out a single number or a scalar value, right? This is how it does it. Now, what's fascinating about this particular scalar function is that if I go ahead and compute its gradient, right, that just means take the derivative with respect to x, take the derivative with respect to y, take the derivative with respect to z, and actually you see, you get this. And this, if you compare with our vector field, this is v. So in this case, this function f is actually a potential function for the vector field v. And again, we say a because, as you can kind of see, there's no guarantee that this is actually unique. In fact, if you have some arbitrary alpha constant here, you can have an infinite number of potential functions. All of them have the property, though, that when you take its gradient, you obtain the vector field in question. So in this case, here is the vector function here's the scalar function that is the potential function for the vector function v. And I'm sure you're asking yourself right now, this seems a little fishy. Where did you get this? Did you just pull this thing out of thin air, right? And we're going to explore that in just a second. So hold that thought, give me a second to erase the board, and let's talk about now another concept. Okay, so now I'd like to take what appears like a little bit of a sidestep, but I promise you this is totally related. I want to talk a little bit about, do you remember from high school calculus, the general, fundamental theorem of calculus, right? So the idea with the fundamental theorem of calculus, right, is if you're trying to evaluate the integral of some function and you're trying to look at a definite integral from the lower limit of a to the upper limit of b, right? In order to do this, what you were trying to do was basically to find an antiderivative or some function g such that when you take the derivative of g, you get f, right? This g is the antiderivative of f, so to speak. And then what that antiderivative allows you to do is, if you want to evaluate this integral from a to b, you just have to evaluate the antiderivative at x equals b and subtract from the antiderivative evaluated at x equals, that should be an a. Right? right? That's the idea. Oh, and again, maybe this is a great time to point out that I have lecture notes for all of these. So if you want to follow along in a nice PDF with code and nice notation, so you don't miss, so I don't make these kind of little mistakes, feel free to check out the link in the description of this video. There's a link to a page where you can get all the artifacts of this lecture, so you can follow along in a little bit more clean fashion. But anyway, that's the idea, right? You just evaluate the antiderivative at the two limits, and the difference gets you the integral that you're interested in, right? So the process for computing a definite integral, right? It's a two-step process, right? So first is you got to find this function g, right? This antiderivative, and this g has the special property that its derivative is equal to this integrand f, right? Then once you have that, all you got to do is evaluate the difference of g between x equals b and x equals a, right? As this two-step process. So alternatively, right, maybe you could write this up here in kind of shorthand notation like this, right? It's just the integral of f from a to b, it's just g evaluated at b minus g evaluated at a, right? So that's all you're doing. So remember, that was your normal standard fundamental theorem of calculus. So where this extends now to line integrals is, let's go back and consider our general line integral, right? Where I had some line integral over a path C through some vector field f, right? This was our line integral, right? Now, let's label this as equation 2, okay? Now, the question in a line integral perspective, right, if we keep in mind what we just discussed, the fundamental theorem of calculus here, is when can we maybe consider the integrand, right? When might that integrand here be considered to be the derivative of another function, just like we were doing over here, right? Well, it turns out that you can consider the integrand, right, which was this vector field f, to be the derivative of another function when you have a potential function which basically derives this vector field, right? So if this is true, if your vector field f here is actually coming from the gradient of a potential function, some interesting things happen, right? So let's see what happens if equation 3 here is true. In other words, what if we're dealing with a vector field or a vector function f, which comes from a potential function lowercase f, okay? What happens when that's true? So again, let's just look at this line integral when this is true, okay? So I'm just going to write that here. So here's their general definition of the line integral. Remember, again, this was this was the idea of a line integral, and then over here is how you actually compute it, right? Remember, we talked about this in the line integral discussion. The way you actually compute this is you evaluate the vector function at the parameterization, right? You're going to parameterize the curve R, the curve C, using some parameterization, which we're calling R in this case. So in other words, you got to evaluate the vector function along the parameterized path, and then you got to dot it with R prime of t, right? And remember, the parameterization, it's just saying that the x and the y value, so in this case, we're going to look at this in 2 dimensions, just x and y, but this idea directly extends to 3D or arbitrarily higher dimensions, okay? I'm just going to use 2Ds just for ease of simplicity. So remember, the parameterization in 2D just says all the x values are some function of t, all the y values are some function of t, okay? So therefore, R prime in this equation up here, it's just take the derivative of those parameterizations with respect to t, right? This is what we did in the line integral video last time, okay? So let's plug this R prime into here, okay? So this is actually pretty easy to do. Just plug that in here, okay? That yields this, right? So now, here, we've got this. Now, at this point, we can ask ourselves, is there anything special about this vector function f? Well, now let's go ahead and plug in, what if this vector function f comes from the gradient of a potential function, okay? So all I'm going to do now is, for this term here, substitute gradient of the potential function, right? And remember, gradient of this potential function we said was just partial of the potential function with respect to x, and then partial of the potential function with respect to y, right? So that gets substituted in right there, okay? And now you see, all we have is we have a dot product of 2 vectors, okay? So take the dot product of this, you end up with this, okay? Does this look familiar? Remember, from our chain rule discussion, this is actually the same thing as the derivative of f with respect to t. right? So f is our lowercase, it's our potential function, right? Okay, so again, if you need a refresher memory on the chain rule, we've got a dedicated video on that, but you'll see that this is true. This entire thing boils down to just how does the potential function f change with respect to my parameterization variable. So this entire thing can get plugged in for the integral. And now, this is where the magic happens. Compare this here with what we were doing over here, right? Basically, it's this, right? Do you see how we basically got, you know, this, we could have written this as, right, dg dx, right? Or in our case, we have df dt, right? But these are the exact same thing, right? We basically are showing now that lowercase f is effectively the antiderivative, right, of this integrand. So now to compute this definite integral between a and b, I just have to evaluate the potential function f at b minus a, right? That's all I'm doing, right? It's basically now we're just applying normal fundamental theorem of calculus. And again, what we maybe should be a little bit clear of, this is a little bit hand-wavy notation right here. You got to remember this function, this potential function f, it's a function of x and y, right? It's a scalar function. So really, what we mean when we say f of b minus f of a, this is really f evaluated at the parameterization at b minus f at the parameterization at a. So I guess if you really wanted to be even more explicit, this is really f when x is evaluated at b and the y value is evaluated at b, right? Minus f when the x value is at a minus the y value at a. So this thing in red is the very, very explicit way to actually compute this right-hand side. But often this is a little bit cleaner, or maybe this. So anyway, let's box this up, okay? Okay? So what's really fascinating about this, right? Let's step back and ask ourselves, is there any kind of interesting, ramifications of this? If you think about this, what is this saying? It's saying the line integral over some arbitrary path c actually only depends on the potential function value at b minus the potential function value at a. In other words, it's independent of the path. So as long as you have multiple paths, for example, you start here at A and you end here at B, right? Here's one potential path, C1, right? And here's another one, C2. And maybe a third, C3. All of these have different paths, but they all end up at A minus B. And if you look at this equation down here, it's basically saying, I don't care what path you took. I only care about the starting and the ending point of the path. And as long as those two are the same, the line integral is going to be the same. The numerical value is the same. It doesn't matter which way you get there if the start and the end points are the same. So that's actually interesting, and that's what I think we want to investigate a little bit. Give me a second to erase the board, and we'll take a look at that next. All right, so let's look at an example of how we can find and use a potential function to help us with this line integral. So just as a quick note, before we jump into this example, in the notes and some other author's notation, you may see this angle bracket A comma B and another angle bracket. So in this particular context of this example in this discussion, I'm using this to denote a vector. So this is a two-element vector with A in the x component and B in the y component. This doesn't mean dot product. I know sometimes you see the angle brackets used for dot product, so hopefully the context will make sense, but I just want to call that out right now. So what I mean by that is let's consider a vector field and a curve. So the vector field looks like this. So here's the x component and here's the y component. So again, you can think of this as like f in the x and here's f in the y. So again, I'm using this angle bracket notation just to save a little bit of space, okay? And then I also want to consider, okay, I've got a curve going through this vector field. The curve is parameterized with respect to t. So the x components are this, it's e to the t sine t, and the y values do this, e to the t cosine t. And I'm going to let t run between 0 and pi, okay? So that's the picture, and in fact, here's a physical picture of it over on the side. This is what the picture looks like. I just sketched this up in Mathematica, so you can see there's a curve going through this vector field, and the vector field is changing. So the question is, in this context, let's go ahead and compute the work done by that vector field to move a particle along that curve C, just like we talked about in our last video. In other words, I want to compute this line integral right here, okay? So at this point, we've got two options. Option one is, let's just do it by brute force, right? Just use what we talked about in the previous video to just compute the line integral via brute force, right? So just, we have all of these terms, we've got everything, right? I've got a parameterization R, so I can calculate R bar by just differentiating this thing. I could then plug in my parameterization R into this vector field F here, and I can compute this dot product, I can do the integral. Anyway, la la la, you could do all this, turn the crank. That's why I've got this dot dot dot. If you want to see the nitty gritty details, check out the notes, but you turn the crank, turn the crank, turn the crank, and you can brute force this thing and get this as your answer, right? 1 plus e to the 3 pi. That's the number, right? Okay. The other way we could potentially do this, now that we understand this idea of potential functions and the fundamental theorem of calculus applied to line integrals, is we could now look at trying to skin this cat another way. The way we're going to do this is, let's ask ourselves, can I find a potential function lowercase f such that when I take its gradient, I get the vector field f, big F, that I'm interested in, right? That's what I'm looking for. I'm looking for this little function f. And again, you got to remember this function, right? It's a function of x and y, right? So let's just expand this. So the left-hand side, I take this function of f of x and y, I take its gradient, it just looks like this, right? Here's the gradient. It's the partial of f with respect to f and the partial of f with respect to y. It's a two-element vector. I need this to equal this two-element vector in particular, right? There we go. So why don't I break this up into two equations? So here's one equation in the top, right? Let me just draw a line through this, and the top one I've written right here. Let's label this as equation A, and the bottom one here is just equation B. So two separate equations. I'm looking for a function f which will simultaneously satisfy equation A and equation B, okay? So how can I go about doing this? Again, there's two now ways that we can go around doing this. So let's look at method A, which I kind of refer to as integrating both equations. So let's just start with equation A here. Look at this, and let's just integrate both sides with respect to x, dx. Okay, so that's what I've written down here, okay? So as you can see, the nice thing about this is the left-hand side just turns into f, right? And the right-hand side, I can actually go ahead and integrate this. So I integrate this, and you get this, right? You get this integral of 3 turns into 3x, this integral of 2xy turns into x squared y, and then you got to remember there's a constant of integration associated with it. Now the one trick to this is that, think about this, we're integrating with respect to x. So this constant of integration here, it's actually not a constant. It can be a function of y. As long as it is not a function of x, by the time I take the derivative of this, or the partial derivative of this with respect to x, I will recover this integrand term here, okay? So again, the one thing to note, I'm going to call this constant of integration g as a function of y, right? So it's some function of only y, okay? Now, let's do the exact same thing with equation B right here. Let's just go ahead and integrate both sides with respect to y now, okay? dy. That's what I've done over here. And again, it's the exact same story that you end up with this plus a constant of integration. But this constant of integration now, because I'm integrating with respect to y, this term can have x's in it, but no y. So I'm going to denote this as h of x to denote it's only a function of x. Okay, so now what we've got is you basically have two expressions or two candidates for f. Those two that I've underlined in blue. Let's just set them equal to each other. I need f to equal f. I need both of these to be consistent. So it's just this term has got to equal this term. So that's what I've got right here. And if you stare at this now, you see that, hey, some of these things cancel out. You end up with this. So now I've got this expression, and voila, I'm actually in luck now, because I see that, okay, in order to make this true, I see that, okay, g of y just has to be, here's a term that is only y's, and then h of x over here, here's a term that's only x's. So if I choose g of y to be this, and I choose h of x to be this, you end up with this equation right here, and this here turns out to work, right? This is the potential function, lowercase f, that when I take its gradient, you will actually recover the vector field big F, okay? So that's awesome. That's one way to do it. The second way you could also go about trying to find this potential function is, I'm going to call this method B, is we can integrate one of those equations with respect to x and then differentiate with respect to y, or vice versa, or flip-flop. It's all similar. Let's look at an example of this. So let's go ahead and start again with a. In fact, let's do exactly this. Let's start by integrating with respect to x, right? Remember, that got us down to here, right? That's this term, right? So I'm just going to copy that over here. So I'm going to ... skip the steps. I think we see how we got this. I got this by basically integrating equation A with respect to x. Now what I'm going to do is I'm going to differentiate this whole thing with respect to y. So take the partial of this with respect to y, partial of this with respect to y, okay? So you end up with this. And you can see that if I take the partial of this with respect to y, like this guy goes away, right? Because this has no y's in it. And then we just end up with x squared here. And then you have to take the partial of this with respect to y. So that's what I've written right here, okay? Now, I need this. Here it is. It's partial of f with respect to y. That's this term right here, right? So it has to equal this second component here. So just set those two things equal to each other right here. And again, you see this cancels and this cancels. So we end up with this expression here. And now what we see is we're searching for a function g, which can only be a function of y, but this thing also has a special property that when I take its derivative with respect to y, I end up with minus 3y squared. And I think you can see by inspection, if I just choose, whoopsie, hold on a second, did I, so I think I've messed this up. This should just be a minus y squared, right? Yeah, there we go. Right, because when I take the partial of this thing with respect to y, yeah, the 3 drops down to the, yep, this works out. Okay, there we go. So now I can plug this back up into here, right? This now becomes minus y cubed. And again, we end up with the exact same result we had here, right? So either way you do this, what we've done here is both of these techniques have successfully yielded a potential function for this vector field f, okay? So with that, now we can go ahead and apply the fundamental theorem of calculus to get the same, to evaluate the line integral in a much cleaner, quicker way. Okay, so I erased the middle of the board, but I kept most of this. This is the previous result, and I also moved our potential function that we just found down to this little corner. And now let's use that potential function to evaluate the line integral. So what we showed earlier is that now the fundamental theorem of calculus basically gave us that this line integral, all I have to do is evaluate the potential function at point B and subtract it from the potential function at point A. And again, this was sort of the hand-wavy notation of just saying potential function of B minus potential function of A, right? But really, we see that, okay, this is really talking about the potential function evaluated at the parameterization at A minus the parameterization at B, right? Or even one step more explicit, right? We see, right, the potential function is a function of x and y. So I need to find the x and the y locations at either point, right? So really what this here is the potential function evaluated at the parameterization x at b and the parameterization y at b minus the parameterization of x at a and y at a, right? So this is the explicit formula of it, and I guess this is a little bit more complete and explicit, but this is a lot easier to just conceptualize, okay? So the first thing we need to do is we need to figure out what are the parameterization values at point A and point B, right? So that's what this is, right? So the parameterization at point A, so remember, point A was t equals 0, right? So all we have to do is come back to our original parameterization right here, right? I just need to evaluate this at point, here's point A, and here's point B, right? So just plug in this equation, everywhere you see t, replace it with 0. That's what you end up with here, and you boil it, do all the math, and here's the point, right? Point 0, 1. So that's the place where the path starts. And again, that makes sense with the picture we saw earlier. Similarly, I can evaluate the parameterization at t equals b, right? And again, that's just take this expression here, everywhere you see a t, plug in the b value, which in this case is pi, and again, you turn the crank, you end up with this. So here we go. Here is the 2 points. So this, again, just to make sure we're explicitly clear, this is the x position at point A. Here is the y position at point A. Similarly, here is the x position at point B, and here's the y position at point B, right? Okay, great. So now we've got these. Just plug them into now the potential function, right? So all we have to do is, like we said, here's the potential function, plug in those points into the potential function. So this term here is you take your potential function, everywhere you see x, plug in this value, right? Everywhere you see y, plug in, oh, sorry, excuse me, I'm pointing to the wrong thing. See, I got myself confused, right? This is the point at B. This is R at point B, right? So actually, this first term here is you take the potential function, and everywhere you see x, you plug in that value, right? Everywhere you see y, you plug in that value, okay? That gets us this whole thing. And then similarly, this here is just the potential, the potential function evaluated at R, A, right? Okay, so same thing. Everywhere you see an x in the potential function, plug in this value. Everywhere you see a y in the potential function, plug in that value, okay? That gets us this term in parentheses, and you boil it down to the end of the day, this whole gobbledygook turns into e to the 3 pi. This right over here turns into just a positive 1, and voila. This here is your line integral value, which if you compare with what we got via the brute force method, they're the exact same thing, right? So this is actually pretty fun, right? So in this, well, in all cases for this, it doesn't matter the curve you take or the path you take. It doesn't matter what this parameterization C is, as long as it starts and ends at the same location, the line integral value is the same. And just to further reinforce this idea, in fact, in the notes, I've got another example here. I'll show you a picture of this right now. I've got an alternative parameterization of a different, instead of taking this kind of curvy path to get from point A to point B, let's just take a straight shot line going straight down to point A to point B. So that's what I'm showing over here in this alternative kind of red line. And again, what you can do is, I'll leave this as an exercise to you, or just check out the lecture notes. I've got the calculations there. Is, again, you could brute force calculate the line integral of this red path, and you'll end up with the exact same option. In fact, you take any path and you calculate the line integral, you're going to come up with the same result. So it's kind of interesting, right? Now, I'm sure this is naturally leading you to the question of, okay, this is all fine and good, but are there situations where this is not the case, right? And what does that mean? So what actually happens is, if there is a case where the line integral depends on the path, you're going to see that this process that we just walked through to try to find a potential function, you're not going to be able to find a potential function which is going to yield that vector field. So again, in the interest of time, I'm not going to write it all explicitly out on the board. It's all in nitty-gritty details here in the notes, but here's another example. I'll just show you a picture. This is a pretty benign looking vector field, right? It doesn't look like much. It's pretty darn simple, okay? It's just a sort of circular swirling vector field. But what's interesting here is, in this vector field, the amount, or effectively the line integral calculation is going to change depending on how you get from the starting to the end point. So for example, here's two paths, a C1 and a C2. Let's just consider the C1. If you look at the C1, we could actually even just kind of think it through using kind of engineering reasoning, right? If you look at how this C1 is oriented with respect to the vector field, make the observation that what's interesting is the vector field is actually perpendicular or normal to the curve at every single point in the curve, right? Because this line is just kind of going straight across, right? I think you can convince yourself that actually, if the path of travel is perpendicular to the force, there's actually no work being done along this cyan C1 straight curve, right? So actually, if you took the line integral over this C1 path, you should expect to get 0. Now contrast that with the other curve, the red curve, right? It starts and ends in the exact same position, but what you can see is it's sort of going along the direction of the vector field all the time. So as you do basically a force times a distance, calculation as you're moving along this, you're seeing you're accumulating work along this path. So that same path, or excuse me, that path which has the same start and ending point is going to have a different line integral value. So again, it's here in the notes if you want to see that happen. And what happens here is if you try to find a potential function using the techniques that we just talked about previously, you're going to run into an inconsistency and you're not going to be able to find a potential function whose gradient derives and generates this vector field. So it's kind of interesting. That being said, that leads probably to our next and final discussion point. So give me a second to erase the board and let's tackle that next. Okay, so let's state this formally. So this idea of path independence of line integrals, it's also sometimes referred to as the gradient theorem. And again, just to state it, what we're basically saying is, like we saw earlier, if you have a vector field f, which is a gradient of some potential function, right, then the line integral is only dependent on the potential function at the endpoint and the potential function value at the start point, okay? So this is basically it. And again, if you're interested, we kind of did the proof of this, at least one direction of the proof on the board here. If you want both directions of the both kind of if and only if implication of this, it's here in the lecture notes, but I just wanted to state that formally. It's called the gradient theorem. That's something else you can look up. There's a lot of previous references on this, but this is the general gist of it. Okay, so this also sometimes you'll run into some other terminology in terms of conservative vector fields or exact vector fields. Maybe we should just mention that to be comprehensive about this. So a vector field, if you have this field that it is the gradient of a potential function, it's called an exact vector field. So that's the terminology. So an exact vector field basically means you have a vector field which is a gradient of a potential function. That implies that f is exact, right? This is almost by definition of exact. That's just another way to call this vector field which came from a potential function. You can call it an exact vector field. What you'll also hear in lots of engineering and math circles is the idea of, okay, a conservative vector field. So a conservative vector field is one where the line integral is independent of the path, right? It doesn't matter how you get from point A to point B. The line integral value is not going to matter. If you're in a vector field where that's true, that's called a conservative vector field. And we basically see here that the idea of conservative and exact, often the lines are blurred because they are they're basically the same thing, right? So what we can observe is that for these conservative / exact vector fields, there's a couple of interesting things that happen, right? One observation we saw is that, well, just by definition, the reason we call these things, why we're so interested in them, is these vector fields come from the gradient of some potential function, and now we know how to compute those if you're able, right? So this is a really nice feature because what that buys us is we end up with a lot of handy ideas. So what we just showed that is if you have a conservative vector field, then the line integral value only matters on the starting and end points of the potential function. And actually, we mostly showed, like I said, that implication where if you have a conservative vector field, this is true. It actually also goes backwards, right? If the paths are all independent, then it shows that f is conservative and therefore is the gradient of some potential function. So this is an if and only if implication. And again, the proof is in the notes if you're interested in this. The direct extension of this, actually, another way you could state this is that if f is conservative, then a closed line integral. So what this basically means, right? So again, I put the little circle here. For those of you who are not familiar with this notation, right? The integral with the close, or the circle, basically means you have some curve C, but the idea with this curve C is that it starts and it ends at the same point. So again, you can go however you like, as long as it provides a closed path. Well, in that context, right, we see that we start and we end at the exact same point, so the difference in potential function is going to be 0, right? So again, this is an if and only if implication, where if you have a conservative vector field, the closed integral is 0, or if any closed integral you take around any path is 0, then also you have a conservative vector field here. Okay, so interesting. The last thing I want to touch on is, you remember our discussion earlier where we were talking about the curl of a vector field? So if you recall that video, we talked about how if you have the curl of a gradient or this was true by definition by any function f. If you take its gradient and you take its curl, you get 0, right? So in this case, if we say, okay, if I have a vector field f, which is actually this gradient of this function, like we're talking about here, this vector field f, it's irrotational, right? It doesn't have any of this rotation idea, right? So what we're now seeing is we can combine all of these, and we can basically say that, okay, if f is conservative, right, meaning that the vector function came from the gradient of some potential function, then we know that it's actually irrotational as well, right? The curl of that vector field is going to be 0, right? And actually, the implication goes the other way as well if the domain that you're interested in is what's called simply connected. And basically, again, I've got a discussion of that in the notes. You can look this up. It's a fairly reasonable idea. Wikipedia has an excellent article on simply connected. But as long as your domain that we're doing all of this analysis and integration on doesn't have any like holes in it, then the implication goes the other way. This is almost a more useful one, right? It's like, if someone hands you a vector field f and you take the curl of it and you come out with it being 0, you know that vector field is irrotational, and the implication now is that also the vector field f is conservative. Whoops, sorry, I missed a bar here. Right? It's conservative, right? And therefore the line integrals are all only dependent on the difference between the start and the end point, right? So there you have it, a follow-on to our line integral discussions. I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel or hitting the like or basically leaving a comment. That really does help with the algorithm on the YouTube engine. And like I said, the new videos come out every single Monday, so I hope I'll be able to catch you there and we can all have a nice, fun discussion on engineering and science. So until then, I think I'm going to sign off. Talk to you later. Bye.